Scientists found a planet 40 light years away. It has a rocky surface, it is the right size, and it maintains the right temperature for life as we understand it. Liquid water might actually exist there on the surface, sitting beneath open skies and pools and lakes and possibly vast oceans. For years, the entire scientific community agreed this world was the one. This is the planet most likely to harbor life beyond Earth, the best candidate we have ever discovered in our search for worlds like our own. So they pointed the most powerful space telescope ever built directly at it. They aimed James Webb, the telescope that cost $10 billion and took 30 years to build. The telescope designed specifically to answer this one single question that has haunted humanity since we first looked up at the night sky and wondered if we were truly alone. Are we alone? And after years of observation, after processing data so complex that it took entire teams of scientists working around the clock for months on end, after developing brand new mathematical techniques that nobody had ever tried before in the entire history of astronomical data processing, the answer they got back was not yes. It was not no. It was something far more disturbing and unsettling than either simple answer could possibly be. They literally cannot tell, not because the telescope failed, not because the planet is too far away for our instruments to reach, but because the star this planet orbits is doing something that is breaking science in ways nobody fully predicted when they planned these observations. The story of what is happening around this star right now is one of the most important and most unsettling stories in the entire history of astronomy. A story that will reshape how we understand habitability across the galaxy. The planet is called TRAPPIST-1e. To understand why this planet made every scientist on Earth stop what they were doing when it was discovered, you need to know why it matters so much to our search for extraterrestrial life. 40 light years from Earth is basically next door in cosmic terms. Our galaxy alone spans 100,000 light years across from edge to edge. 40 light years is practically our backyard. And sitting in that backyard is a star called TRAPPIST-1. It is small and dim in red, a color that seems almost ominous as you learn what it means. It is roughly the same physical size as Jupiter, but made of star stuff, dense and massive and burning with nuclear fusion deep in its core. And packed in close around this tiny red star are 7 planets. 7 rocky, Earth-sized worlds, all orbiting their star in the same amount of time it takes you to go on a weekend trip. The innermost planet completes a full year in about 1.5 Earth days. The outermost takes 19 days to complete one orbit. Every single one of those 7 planets orbits closer to their star than Mercury orbits our sun. Think about that for a moment. Every planet in this entire system sits inside the orbit of Mercury. The entire system, the star and all 7 worlds, would fit inside the orbit of Mercury with room to spare. It is a compact, tightly packed arrangement unlike anything in our own solar system. You might think that planets orbiting so close to a star must be burning hellscapes, worlds with molten surfaces and crushing heat that no life could possibly survive. But here is the thing that changes everything and makes TRAPPIST-1 so special. TRAPPIST-1 is not our sun. It is not a massive ball of heat and light that would incinerate anything nearby. It is tiny. It is cool. It is dim. It is so dim that you would need to stand roughly where Mercury sits in our solar system, much closer to our sun than Earth is, just to feel the same warmth we feel here on our home world. This fundamentally changes where the habitable zone sits for this star system. The habitable zone is that special distance from a star where liquid water can exist on a planet's surface, where temperatures are neither too hot nor too cold for life as we understand it. That habitable zone, the distance from a star where this perfect Goldilocks zone exists, sits very close to TRAPPIST-1. And 3 of those 7 worlds sit right inside it. TRAPPIST-1, E, 1F, and 1G, 3 potentially habitable planets, all orbiting the same star, all close enough that a powerful telescope might actually be able to analyze their atmospheres from Earth. No other known star system gives us this opportunity. 3 Earth-sized worlds in the habitable zone, packed close enough to their star that telescopes can study them dozens of times per year, gathering data with each pass across the star's face. This is why the discovery became front-page news around the world in 2017. Scientists were stunned. This is why scientists called TRAPPIST-1 the most important planetary system in modern astronomy. This is why, when James Webb launched on Christmas Day 2021, TRAPPIST-1 sat near the very top of its observation list, a priority target that would receive thousands of hours of the telescope's precious observing time. The story of how this system was discovered is almost as extraordinary as the system itself. A Belgian astronomer named Michael Gillen was running a survey in the Chilean Atacama Desert, one of the driest places on Earth where the air is thin and clear and perfect for astronomy. He was not using a massive cutting-edge observatory with billions in funding behind it, but rather a modest 60-centimeter robotic telescope, an automated instrument that could observe night after night without a human operator present. He had named it TRAPPIST with affection, a tribute to the Trappist beers brewed by monastic orders back in Belgium, a whimsical name for a scientific instrument searching for worlds. He had a list of about 50 nearby ultra-cool dwarf stars to monitor, looking methodically for tiny dips in brightness that might signal a planet passing in front of one of them. Around the 30th star on his list, the telescope caught something unusual in the data. A dip in brightness, then another, then a cluster of dips coming so frequently and so regularly that they could not all belong to the same object. Multiple things were transiting this star, multiple planets orbiting the same small red sun. Gillen brought in more telescopes, ground-based observatories across multiple continents, all pointed at the same tiny red star, coordinating observations to confirm what he had found. In May 2016, his team published their first results: 3 Earth-sized planets orbiting an ultra-cool red dwarf just under 40 light-years away. Exciting, certainly, but not yet extraordinary enough to shake the world. What made it truly extraordinary was what happened next. NASA's Spitzer Space Telescope locked onto TRAPPIST-1 and stared at it continuously for 21 days. 21 days of uninterrupted observation, watching the same star without blinking, recording every subtle change in its light. Buried in that massive stream of data were 4 more planets that ground-based telescopes on Earth had completely missed. In February 2017, Gillen's team published the full picture: 7 Earth-sized rocky worlds orbiting one single star, 3 of them sitting in the habitable zone. The astronomical community was astounded. The orbital arrangement of these 7 planets is mathematically beautiful in a way that tells you something profound and remarkable about the system's ancient history. All 7 worlds are locked together in what astronomers call a resonant chain, a configuration so precise and so stable that it seems almost impossible. For every 8 orbits, the innermost planet completes around the star. The second one completes exactly 5, and the pattern continues outward through the system in perfect mathematical harmony. Each planet's orbital period falls into a neat ratio with its neighbors, a cosmic music box playing notes that have remained in tune for billions of years. It is the longest unbroken chain of this kind of orbital resonance ever found around a single star, a record that speaks to the stability and organization of the system. The planets migrated inward through the disk of gas and dust they formed from billions of years ago, and they clicked into place one by one like beads sliding onto a wire, locked by gravity into positions they have held ever since. The chain has held ever since for an estimated 7.6 billion years, a span so vast it is difficult to comprehend. That makes this system roughly 3 billion years older than our own solar system, giving it additional time for chemical complexity and possibly life to have emerged. This resonant structure also allowed scientists to weigh each planet precisely without ever actually resolving any of them as anything more than a tiny dip in starlight. As the planets pass each other in their orbits, they exchange tiny gravitational tugs that cause their transit timing to shift by seconds and minutes from what pure orbital mechanics would predict if they existed alone. By measuring those tiny timing variations with extraordinary precision, astronomers could calculate exactly how massive each world is, unlocking information about their composition. And the masses told them something critical and defining. These planets are rocky, dense, with solid surfaces. Not gas clouds, not ocean worlds with no floor, not impossible structures. Actual rocky planets with surfaces you could theoretically stand on, with gravity that would hold you to their ground. TRAPPIST-1. E specifically sits right in the sweet spot of the habitable zone, a position almost perfectly calculated by the laws of physics and orbital mechanics. It receives about 2/3 of the energy from its star that Earth receives from our sun, warming it enough for liquid water, but not so much that all moisture would evaporate into space. It is the right temperature. It is the right size. It is rocky. It is the most Earth-like candidate world we have ever found anywhere in the universe despite decades of searching. James Webb was designed specifically to look at it and answer whether it harbors an atmosphere. Here is the dream scenario that scientists had in mind when Webb launched on that Christmas day in 2021. Light from TRAPPIST-1 passes through the thin shell of TRAPPIST-1E's atmosphere as the planet crosses in front of its star, a moment that happens regularly and predictably. Different gases absorb different wavelengths of that light, each one selective about which colors to capture. Water absorbs certain wavelengths of light. Carbon dioxide absorbs others. Methane, oxygen, sulfur dioxide, each one has its preferences. Each one leaves a distinct fingerprint in the light, a signature that scientists can read. By analyzing those fingerprints, Webb could tell us exactly what gases exist in that atmosphere from 40 light-years away, without ever sending a single spacecraft anywhere near the planet. It is genuinely one of the most remarkable techniques in the entire history of science. And it works. It has worked beautifully on large, puffy, gas giant planets whose thick atmospheres leave strong, obvious signals that are unmistakable. The question was whether it could work on small, rocky planets whose thin atmospheres would leave signals roughly 100 times fainter, on the edge of detectability. The answer for TRAPPIST-1e specifically turned out to be not yet. And the reason why is something nobody fully anticipated when these observations were planned. The star itself, TRAPPIST-1, is magnetically volatile in ways that astronomers did not fully appreciate beforehand. Its surface is constantly shifting and churning, covered in dark star spots and bright hot patches that rotate in and out of view as the star spins. Our sun has sunspots too, and they can be quite large by Earth standards. But the sun is so incredibly large and bright that a few dark patches barely register when you are trying to measure the faint atmospheric signal of a transiting planet. On TRAPPIST-1, which is tiny and dim to begin with, a significantly smaller target, those spots and bright patches cover a significant fraction of the visible surface, and they change on timescales of days and weeks. Sometimes, during a single transit observation lasting a few hours, the star's face looks noticeably different at the end of the measurement than it did at the beginning. This matters enormously because of what it does to the data. When scientists measure the light from a transit, they are comparing the star's brightness during the transit to its brightness outside the transit. Any change in the star's surface creates a false signal that mimics the kind of atmospheric absorption they are looking for. Scientists call it stellar contamination, and it is the enemy of everything they are trying to accomplish. On TRAPPIST-1, that contamination arrives at amplitudes of hundreds to thousands of parts per million, a staggering amount of false signal. The atmospheric signal from a thin rocky planet's atmosphere, at most, is about 100 parts per million. The noise is 10 times louder than the signal scientists are trying to detect. It is like trying to hear someone whispering your name from across a massive stadium while a rock concert is playing at full volume right next to you, drowning out everything else. It is worse than ordinary noise because this stellar contamination is not random static that you could average away with time. It mimics the exact shape and pattern of the signal you are trying to extract. It contaminates the data in the same wavelengths where atmospheric gases would leave their fingerprints. You cannot just filter it out the way you would filter static from a radio signal because the interference and the message look too similar to your instruments. Then, during one of the Webb observations of TRAPPIST-1e, a massive stellar flare erupted mid-transit, a sudden outburst of magnetic energy. A burst of energy from the star's surface dumped an enormous signal into the data that bore no resemblance to anything a planetary atmosphere would produce. One entire transit observation, gone, corrupted, beyond salvage, ruined by the star's tantrum. The researchers spent more than a year developing brand new mathematical techniques to try to separate the star's noise from whatever the planet might be contributing. New frameworks, new models, new approaches to data processing that had never been tried before in the history of astronomy. And after all of that work, after months of dedicated effort, the honest conclusion was this. They could not say with confidence whether TRAPPIST-1e has an atmosphere or not. The data simply would not allow them to make that determination. While the campaign to observe TRAPPIST-1e was struggling with stellar noise, Webb was also looking at the other planets in the system, and those results were cleaner, devastatingly, heartbreakingly cleaner. TRAPPIST-1b, the innermost planet, was examined first. Scientists used Webb's MIRI instrument to measure the planet's thermal glow at a specific wavelength, where carbon dioxide absorbs light very strongly. If TRAPPIST-1b had a thick carbon dioxide atmosphere the way Venus does, its thermal glow at that wavelength would have been noticeably dim by the blanket of gas overhead. The measurement came back bright and clean. A thick atmosphere was ruled out at greater than 6 sigma confidence. In statistics, 6 sigma means you would expect to be wrong about 1 time in 500 million. The innermost planet of TRAPPIST-1 is a bare, airless rock, TRAPPIST. 1c, the second planet, received similar treatment. Results pointed strongly away from a thick atmosphere, though not quite as definitively. Then, in April 2026, a paper published in Nature Astronomy delivered full thermal phase curve measurements for both TRAPPIST-1b and TRAPPIST-1c together. A thermal phase curve tracks how a planet's brightness changes as it rotates and shows different faces to the telescope. Both worlds emitted heat in patterns consistent only with bare rocky surfaces. Atmospheres with surface pressures even close to Earth's sea level were strongly ruled out. 2 down, then came TRAPPIST-1d, right at the inner edge of the habitable zone, slightly smaller than Earth. It was the inner planet most likely to have held onto some kind of atmosphere. Published results from 2025 showed a transmission spectrum covering a wide range of wavelengths. After painstakingly correcting for the enormous stellar contamination, the raw data was dominated by signals hundreds to 1,000 parts per million from stellar surface features. What remained was a completely flat line. No methane, no water, no carbon dioxide, no carbon monoxide, no sulfur dioxide, nothing. The lead researcher on that study put it plainly and painfully. TRAPPIST. 1d can be removed from the list of potential Earth twins. 3 of the 7 planets, 3 bare rocks, the inner worlds of the most hyped planetary system in astronomy, stripped clean of their atmospheres by their star's radiation. And this concentrated the entire weight of humanity's search for life around other stars onto one world. TRAPPIST-1e, the habitable zone planet, the one where the math works, the one where temperatures could allow liquid water to pool on the surface, but only if it has an atmosphere. There was a moment in late 2025 when it seemed like maybe Webb had found something. When the research team ran their contamination-corrected transmission spectrum of TRAPPIST-1e through a battery of atmospheric models, they found something unexpected. Models that included methane in the planet's atmosphere provided better fits to the data than models that did not. Not a strong detection, not a clean, unambiguous signal, but a statistical preference, a hint. The data seemed to slightly favor scenarios where TRAPPIST-1e had traces of methane mixed into a background of nitrogen gas. The team cautiously described the possibility. TRAPPIST-1e could be something like a warmer version of Saturn's moon Titan, which has a thick nitrogen-methane atmosphere of its own. They called it a warm exoplanet. For a brief moment, it felt like a breakthrough, like the data was finally quietly pointing towards something. Then Sukrit Ranjan, a planetary scientist at the University of Arizona who had been involved in all 3 of the team's published papers, looked at the result from a different angle. He identified a problem that is almost poetic in its cruelty. TRAPPIST-1 is cool enough as a star that methane can exist in the star's own atmosphere, not on a planet, but in the star itself. The outer layers of an ultra-cool red dwarf are so much cooler than the surface of a sun-like star that complex molecules can survive there. Methane in a star's atmosphere leaves spectral fingerprints that look nearly identical to what you would see if the same gas were sitting in a planetary atmosphere 40 light-years away. So when Webb's instruments detected something that looked like methane, the question that could not be answered was this. Is this signal coming from the thin ring of planetary atmosphere, or is it coming from the star itself, mixed in with all the other stellar contamination they were already struggling to remove? Ranjan was direct about his conclusion. Based on the most recent analysis, the tentative hint of a methane atmosphere is more likely to be noise from the host star than a real detection. He was careful to add this does not mean TRAPPIST-1e has no atmosphere. It only means the current data cannot distinguish between a genuine planetary signal and a stellar artifact. 2 possible stories remained. In one, the planet has no atmosphere at all, a bare, irradiated rock like its inner siblings, stripped of its air long ago by the star's radiation. In the other, the planet has a thin atmosphere, perhaps mostly nitrogen, perhaps with traces of other gases. That Webb's current observations simply are not sensitive enough to detect cleanly above the stellar noise. What is definitively ruled out is a thick, hydrogen-dominated atmosphere, a puffy envelope like a mini Neptune. Webb's sensitivity was more than enough to exclude that. Whatever TRAPPIST-1e is, it has evolved. It is more like Earth or Venus than a gas-rich world. But whether it is a living Earth or a dead Venus, whether it has any air at all, remains locked behind the noise. Here is where science does something genuinely beautiful, even when the data refuses to cooperate. If the star is the problem, and every observation confirms that it absolutely is, then the solution has to involve the star. The team eventually arrived at an approach that sounds almost too clever. They would use a dead world to find a living one. TRAPPIST. 1b, the innermost planet, the one already confirmed to be a bare, airless rock, transits the same star as TRAPPIST-1e. Because TRAPPIST-1b has no atmosphere whatsoever, every single spectral feature that shows up in its transit data must be coming from the star. All of it, every star spot, every bright patch, every molecular fingerprint from the stellar atmosphere. All stellar contamination, nothing else. Because there is no planetary atmosphere contributing anything, which means TRAPPIST-1b can be used as a calibration tool, a stellar noise filter. The technique is called the dual transit method. It works like this. When TRAPPIST-1b and TRAPPIST-1e transit close together in time, you observe both. You record the stellar contamination stamped onto TRAPPIST-1b's transit spectrum. Then, you subtract that contamination pattern from TRAPPIST-1e's spectrum. Whatever signal remains after the subtraction, whatever cannot be explained by the star, is either the planet's atmosphere or the absence of one. Either answer would be a landmark result. Early tests of the technique in 2024 and 2025 showed it genuinely works. In clean observations, the method measurably reduced the stellar contamination exactly as expected. The mathematical principle is sound, but there is a catch. The technique assumes the star's surface does not change dramatically between one planet's transit and the other. When a stellar flare erupts between observations, which on TRAPPIST-1 happens disturbingly often, the star effectively rewrites its own face in minutes. The contamination pattern recorded on TRAPPIST-1b's transit no longer matches what TRAPPIST-1e sees. The filter breaks exactly when you need it most. The team is pressing forward anyway. They have outlined a program requiring approximately 15 dual transit observations spread across multiple James Webb observing cycles. With enough data points, the statistics should overwhelm the noise from individual flare events. Ryan McDonald, one of the key researchers, estimated that the next major update on TRAPPIST-1E's atmosphere should arrive somewhere around early to mid-2027. Beyond Webb, new tools are being built with exactly this problem in mind. NASA's Pandora mission is a small dedicated satellite designed to monitor host stars simultaneously in near-infrared and visible wavelengths, before, during, and after transits. It is specifically engineered to map stellar noise so it can be subtracted from planetary observations more precisely. 3 extremely large ground-based telescopes are currently under construction. They will be able to attack the same problem at much finer spectral resolution by separating planetary and stellar signatures using their slightly different Doppler shifts as the planet moves through its orbit. Further out on the horizon, NASA's Habitable Worlds Observatory is projected for the 2040s. It is being designed from the ground up to directly image potentially habitable planets by suppressing the host star's light by a factor of roughly 10 billion. Not inferring the planet from the star's light, but actually isolating the planet's own light directly. That changes everything. In January 2026, NASA awarded technology development contracts to 7 companies to begin building the engineering required to make it real. So where does this leave us? 40 light-years away on a world that may or may not have an atmosphere, sitting in a habitable zone around a star that will not stop screaming over the signal we are trying to hear, the answer is still locked away. 3 of the 7 planets are dead rocks, that much is certain. And those 3 dead rocks tell us something important and sobering. Red dwarf stars, which are the most common type of star in the entire galaxy, are violent enough when they are young to strip away the atmospheres of their closest planets entirely. The habitable zone planets that survive that early stripping may be the exception, not the rule. If TRAPPIST-1E turns out to be another bare rock, the implications are enormous. The most abundant type of potentially habitable real estate in the galaxy, rocky planets and the habitable zones of red dwarf stars, may not actually be habitable at all. That would mean life, if it exists elsewhere, needs a star more like our sun, which means it is rarer, which means we are more alone than we thought. If TRAPPIST-1E turns out to have an atmosphere, even a thin one, then the opposite is true. Life has a whole universe of potential homes we had not counted on. Every dim red star becomes a candidate. Given that red dwarfs make up roughly 70% of all stars in the Milky Way, each potentially hosting their own tight cluster of rocky planets close enough for telescopes to study, the number of places where life could exist becomes almost incomprehensibly large. One planet, one answer that is still missing. The entire question of whether we are alone in the universe hinges on what is hiding in the noise around a tiny red star 40 light-years from home. James Webb looked at a planet like Earth and something feels off. Not because the planet is wrong, but because the universe is making us work harder than we ever expected just to hear what it is saying. We built the most powerful telescope in human history. We pointed it at our best candidate for life beyond Earth. And the star it orbits is screaming so loudly that we still cannot hear the planet whispering back. The answer is in there somewhere, locked behind the noise and the stellar contamination and all the complications that nature has thrown in our way. We just have not found a way to listen yet, but we are developing new methods and new instruments that will eventually allow us to cut through the chaos and hear the truth. That truth will tell us whether we are alone.